Okay, so far in this unit we have taken a look at pressure, how it's measured, and then we looked at the relationship between pressure and volume, and we referred to that as Boyle's law. It's called Boyle's law because Robert Boyle was the initial scientist who did the experiments with pressure and volume. Well, this next law that we're going to look at is referred to as Charles's law. And Charles's law looks at the relationship between volume and temperature at constant pressure. So what you'll notice is that pressure and volume is at constant temperature. Now we're looking at volume and temperature at constant pressure. Charles's law works the same way that Boyle's law worked, where we had a series of experiments, and then when Boyle looked at the relationship between pressure and volume, he found that when you multiply pressure times volume, you wind up with a constant. Well, with Charles's law, you can do the same thing. You can have a series of experiments, but what we find is that when you look at volume and temperature being equal to that constant, you have to divide the two. So in other words, if you take V1 and you divide by T1 for experiment 1, you get a constant. If you do the same thing for experiment 2, divide those values, you get the same constant. So what we can say is V1 over T1 is equal to a constant, which is also equal to V2 over T2, so we can just write the formula in that form. As with Boyle's law, you can also write it in a modified form. V over T is equal to your constant, and this is just that form written solving for V. Now, one thing that we want to point out here, and this is very important, in fact, probably 90% of the mistakes that people make when calculating using the gas laws is that they forget to change the temperature to Kelvin. Your temperature always has to be in Kelvin, so if you're given a Celsius temperature, make sure you're adding 273 and converting it to kelvins. Whenever you have ratios like this, negative numbers don't work so well, so we like to use a scale that has only positive values, and as you know, the Kelvin scale has only positive values. So let's go through and solve a couple problems the same way we did with Boyle's law. Let's take a look at this one. We've got a balloon containing 1.3 liters. And again, what you'll see me do is write these units as they appear in the problem. So since liters is a unit of volume, I'll say V1 is equal to 1.3 liters. It's at 24.7 degrees Celsius, so T1 is equal to 24.7 degrees Celsius. It's placed into a beaker containing liquid nitrogen at our new temperature, negative 78.5 degrees Celsius, and now we're trying to calculate the new volume. So the first thing that we want to do here is convert our temperatures to Kelvin. Now I know you might be thinking, well, if the units are consistent, what's the problem? Again, remember, we don't want negative values. You can talk to your math teachers about why negatives make ratios a bad scene, but let's just take my word for it. We want positive values. So if we add 24.7 plus 273, we get 297.7 Kelvin. Do the same thing over here. Add 273 to negative 78.5 and we get 194.5 Kelvin. So now we can set up our problem. V1 over T1 is equal to V2, and that's what we're solving for, over T2. And it's not a bad idea to include your units in the problem. That way you'll know after canceling out the other units whether or not you have the right units. So let's do the math. V2 is equal to 0.85 Now the unit there is liters. Remember, your units have to be consistent. So if we start with units or volume units in liters, that means our new volume unit will be in liters. Let's take a look at another one. We've got a gas at 30 degrees Celsius. So I'm going to write T1 is equal to 30 degrees Celsius at 1 atmosphere. Now that's a unit of pressure. So I'm going to write 1 atmosphere. Now notice Charles's law deals with volume and temperature, but if you're given a pressure, write the unit out because you never know when that's going to affect the problem. It occupies a volume of 0.842 liters. What volume, so we're looking for a new volume, will occupy the gas at 60 degrees Celsius, so our new temperature is 60 degrees Celsius, and you can see it's still at 1 atmosphere, so we can cancel that out. Whenever the unit stays constant, you can just cancel it out. So let's do the first thing and convert our Celsius to Kelvin. So 30 plus 273 is 303 Kelvin. 60 plus 273 is 333 Kelvin. So let's set up the problem. V1, 0.842 liters over T1, 303 Kelvin, is equal to V2 over T2, and we're going to solve for V2. We get 0.93, and again, our unit for volume is liters. Let's take a moment here and talk about absolute zero. Okay, absolute zero is the point where we have no molecular movement, and we've talked about this value in previous podcasts. Let's just take a little look at how one way you can determine absolute zero. Let's say you're graphing your data from volume and temperature. In other words, as you lower the temperature of a system, you're plotting its volume. So let's just take water for example. At a temperature of 573 kelvins, water, whatever our sample happens to be, would have a volume of roughly 2.3 liters. As we decrease the temperature, the volume decreases and decreases. So what you can do then is extrapolate that line all the way back until your volume would be zero. Well, you can't have a volume of zero, so theoretically at that point would give you your absolute zero value. And if you do that for multiple gases, what you'll find is they all converge on the same point. At that point, that's where we would call absolute zero, and it shows up at negative 273.15 degrees Celsius. And we'll actually do this lab in the laboratory experience in the classroom. Okay, so first of all we had Boyle's law, and that was written P1 V1 is equal to P2 V2 at constant temperature. Well, now we've got Charles's law, and that's the relationship between volume and temperature at constant pressure. Remember, your units for temperature have to be in Kelvin, and then your units for each of your variables have to be consistent. The next podcast that we do, we're going to take a look at the relationship between volume and moles. Again, as usual, send your questions to hannonandchemistry@gmail.com, and we will talk in the next podcast.